our last lecture, we discussed the mineralogy and crystallography of the precious gemstones, ruby and sapphire. We got right down to the basic building blocks of these gems in order to more fully understand why these stones are so precious. In this lecture, we'll take that information and go a step further in an attempt to understand where and how ruby and sapphire form within the earth. As a brief refresher, the correct mineralogical name for ruby and sapphire is corundum. This is a mineral composed of more than 99% aluminum and oxygen. Now, corundum itself is actually pretty rare in the Earth's crust, and gem-quality corundum is even rarer still. To add some context to this discussion, let's consider the composition of the Earth's crust. The 6 most abundant elements in the crust are oxygen, silicon, aluminum, iron, calcium, and sodium. Aluminum itself actually makes up about 8% of the Earth's crust. Given the abundance of aluminum, it actually seems a bit strange that ruby and sapphire would be so rare. The reason they are so rare is that aluminum really likes to chemically react with other elements present in the Earth's crust. For instance, the most common group of minerals in the Earth's crust are the feldspars. In fact, if we take 5 out of the top 6 most abundant elements in the Earth's crust, oxygen, silicon, aluminum, sodium, and calcium, and put them together, we can make the mineral plagioclase feldspar, which is very rich in aluminum. In fact, this mineral is known to lock up most of the aluminum in the Earth's crust. This, then, is essentially the reason corundum is so rare. Aluminum is a very social atom, and in most cases in the Earth, any aluminum present will want to get together with other atoms to form other minerals. It's actually very difficult to produce an environment in the Earth in which there is so much aluminum present that it has nothing left to react with chemically. Geologists make 2 broad distinctions between metamorphic and magmatic sapphires and rubies. The metamorphic type are those that grew during ancient mountain building events, or orogenic events, during times when continents collided due to the movement of the Earth's tectonic plates. The heat and pressure experienced by geological formations during these events facilitated the crystallization of gem-quality corundum. Metamorphic sapphires and ruby deposits include those in East Africa, Sri Lanka, India, and Myanmar. This map shows some of the ruby and sapphire deposits in Asia. These are mostly metamorphic deposits. Asia has produced some of the most valuable sapphires and rubies, especially those from the mines in Sri Lanka, Mogok, and Kashmir. More recently, metamorphic sapphire and ruby deposits have been discovered in East Africa, in Mozambique, Tanzania, and especially Madagascar, as seen in this map. Magmatic sapphires and rubies were transported to the surface in volcanic events that are not associated with any continental collisions. These sapphires and rubies are generally considered to have formed at great depth and were transported to the surface by basalts and other volcanic formations that happened to pick them up as they passed through the lower depths of the Earth. Major deposits of magmatic sapphires and rubies occur in eastern Australia, Southeast Asia, Africa, and North America. In fact, Africa also hosts some magmatic sapphire deposits in northern Madagascar and further east in Nigeria. Australia, in fact, has been one of the major historic producers of gem corundum. The gem corundum deposits stretch across nearly the entire eastern seaboard of Australia, from lava plains in northern Queensland down to Tasmania in the south. Queensland itself has produced many exceptional sapphires and to this day continues to turn out beautiful gems, especially world-class green, yellow, and blue sapphires. Scientists think metamorphic sapphire and ruby deposits formed when the geological formations containing them weathered out slowly over millions of years and left them behind. This weathering is essential, as most metamorphic rocks containing corundum are very strong, and it would otherwise be very difficult to liberate the rubies and sapphires without risking significant damage to the gems. On the other hand, this is a volcanic rock that would have transported magmatic rubies and sapphires to the surface. This is an example of a sapphire-bearing volcanic rock called a lamprifier from Montana, USA. But in Australia, the rocks are alkali basalts, which are similar in many ways to this rock. One important thing to note with magmatic rubies and sapphires is that they did not actually form in the volcanic rocks that transported them. The rubies and sapphires in this case are called xenocrysts, as they are crystals that are foreign to the volcanic rocks that transported them. How do we actually know that these crystals are xenocrysts? One way we can tell this is by looking at the surfaces of the crystals. On many of these surfaces, we see very interesting geometric patterns that indicate to us that the magmas that transported the sapphires to the surface have actually started to eat away or etch the sapphires. This is seen here on the surface of a sapphire using a special microscopic technique that highlights surface topography with vibrant interference colors. The shape of these triangular etched features is controlled by the underlying symmetry of the corundum crystal structure. These features present strong evidence that these sapphires were merely hitching a ride with the volcanic formations that host them. The sapphires in Australia are not actually mined out of alkali basalts. They are essentially mined out of the dirt and gravel that's left behind after the original formations have broken down. In the very first lecture, we mentioned that corundum is very dense. During weathering, water washes away much of the original rock, but it has a hard time taking away dense materials like corundum. The weathering process then leaves behind a much more concentrated sapphire deposit. Without this additional concentration of sapphires, most deposits would not be economic to mine. The photo here shows bags of dirt containing gem gravel dug out of the earth in which the miners hope to find gem corundum. These bags of payload dirt would be brought to a source of water and washed and sieved in the hopes of finding rubies and sapphires to make all their efforts worthwhile. This photo shows a woman in Madagascar engaged in this endeavor. So we understand how magmatic sapphires and rubies are brought to the surface and what the deposits are like. One lingering question remains, which is how are these rubies and sapphires formed in the first place? The thing is, geologists still don't completely agree on this issue. One way in which scientists are trying to understand these deposits is by looking at inclusions in these sapphires and rubies. These inclusions are minerals or fluids that were trapped with the corundum while it was growing. They are essentially little time capsules that have taken a snapshot of the growth environment when these gems were being formed. In the magmatic type sapphires, we see many different types of inclusions, from minerals like feldspars, needle-like inclusions of iron titanium oxides, to melt inclusions, which are little blebs of magma that was present when the corundum was growing. These melt inclusions, however, represent a much different magma from the basalts that transported them to the surface. The other mineral and fluid inclusions also point to an origin separate from the transporting basalts. While we still may not understand fully what these inclusions are telling us, they provide clear evidence that the sapphires grew in some magmatic event deep within the Earth. Further research will hopefully help geologists clear this issue up. This will allow us to unravel the geological mysteries contained within these wonderful gems.